I recently bought a new car, and when I got it home, I found that it only barely fit in my garage. It was a really tight squeeze, but it would get in there. However, in my garage, I've got a shelving unit at the back, and I have to park my new car very close to it in order to still be able to close the garage door at the back. Now, of course, the parking sensors within the car are really good, and they keep on alarming the closer I get to the shelving unit. However, as soon as I'm within about 60 centimetres, then the parking sensor is beeping about as much as it can. And so after this, I just have to use my own judgment to determine how close I am to the shelves. So I was thinking it would be really good if I could have something that would show me exactly how far I am away from the shelving unit. I put that together with a Raspberry Pi. Let me show you how. Hello once again, Pi geeks and techno nerds all over the world. My name's Jeff, and I'm an IT professional who's been in the industry for over 30 years. I've been using Raspberry Pis ever since they first came out, and I wanted to share with you some of the projects that I've done over the years. If you like what you see on this channel, please hit that thumbs up button, subscribe if you want to see more, and hit that notification bell so you can be told when I put a new video out. Also, let me know in the comments how you get on with this project. And if you've got any ideas for projects that you'd like to see me do in the future, put those in there as well. Now, as I mentioned in the intro, the purpose of this project is to give me a small display that I can put in my garage that will tell me exactly how far my car is parked away from a shelving unit. Now, so far, I haven't crashed into it at all, so my judgment isn't that bad. But it's still very tight. So I just wanted to put something together that could just give me that extra peace of mind so I knew exactly how far I was away from it. And so I was looking around and I found that you can pick up an ultrasonic distance sensor and a small LED matrix really cheaply. And so I then thought I could use a Raspberry Pi to drive both of these things. And since neither needs a lot of processing power, I could get away with using a Raspberry Pi Zero. Now, the one I'm using for this project isn't even a 02W, it's just one of the original Pi Zero Ws. And you can get those now for roughly £15. When you put together the cost of everything for the project, it's roughly around £30 to £35. So price-wise, it's really not too bad, given the peace of mind that it gives me. Now let me go through that kit list in a little bit more detail. The first thing you'll need for this project is the Raspberry Pi itself. Now, as I mentioned before, for this I just used an original Raspberry Pi Zero. You can of course use just about any Raspberry Pi. You could probably also get this to run on a Raspberry Pi Pico, however the programming for it would be quite different, and I'm not going to go into that in this project. The next thing I picked up for this was a case for the Raspberry Pi. Now, so long as you get one that allows access to the GPIO pins, it'll be absolutely fine. So just shop around and get whichever one you like. Now, when it comes to ultrasonic distance sensors, they fundamentally break down into two different types. There's this type here, based on the HC SR04. And what happens with this is that you get a speaker to emit a little pulse of sound, and then you use a microphone to pick up the echo of that sound. The software library that we use to process this can then determine what the delay is between the two, accounting for the speed of sound, and come out with a distance measurement. Now, with the HC SR04, you have to do everything yourself. There is a variant here called the US 100. This works in exactly the same way, in that it does transmit a small pulse of sound and then it receives the echo of that sound in order to determine what the distance is. However, it uses a protocol called UART to provide the communications with the software. Now, UART stands for Universal Asynchronous Receiver Transmitter, and all Raspberry Pis support this natively. Now, I picked up the one that you can see here, and although this is £6.90, compared to the HC-SR04's cost of only £2, I have found the US 100 to be a lot more reliable. It does have a different operating mode based upon a jumper that's on the back of the board, If the jumper's removed, then it will behave like the HC-SR04. If the jumper's plugged in, then it will behave like the US100 and use UART instead. Now, my own experience here has shown the US100 to be a lot more reliable. However, it may just be an aspect of the fact that this board isn't a native HC-SR04 board, so I might have just got unlucky there. However, I did just want to point out that with this behaving as a US100, it's been super reliable, and so I'd personally recommend getting one of these. For the LCD display, I picked up one of these. It's a collection of 4 small 8x8 LED displays that are all strung together to form an 8x32 dot matrix. And for just under £9, I found this to be a complete bargain. Its display is really bright and vibrant, and it works perfectly for this specific use case. Now, the next thing you'll need to do for this is install Raspberry Pi OS onto your Raspberry Pi. In order to do this, you take a micro SD card, and then you can use the Raspberry Pi Imager software to burn the Raspberry Pi operating system onto it. Now, since I'm using a Raspberry Pi Zero here, this only supports the 32-bit version of the operating system. And so I'm using Raspberry Pi OS 32-bit Lite. Depending on which version of Raspberry Pi you're using, you may wish to use the 64-bit version instead. Now, once you've got the operating system installed and you're booted from it, you'll be at a prompt just like this. Now, particularly on Raspberry Pi 1, Raspberry Pi 2 and any model of Raspberry Pi Zero, I always find the best thing to do first is increase the amount of swap space that the Raspberry Pi has available. None of these models have a lot of memory installed, and the last thing that I want to happen is my Raspberry Pi to then crash because it thinks it's out of memory. By increasing the amount of swap space available, you can give it some virtual memory that it uses from the microSD card storage. In order to change this, the first thing you need to do is turn off the swap file. And you do that with this command here, sudo dfizz swap file swap off. You then need to edit the /etc/dfizz swap file. You then want to come down to the line that I've highlighted here, where it configures the size of the swap that's made available. By default, it's only 100 megabytes. I'm going to change this to 2 gigabytes by changing the value to 2048. You then just save the file out. You then need to set up your new swap file space with the command sudo dfizz swap file setup. After that, you can then turn on the swap file again with sudo dfizz swap file swap on. Now, the other issue that I find happens a lot with Raspberry Pis 1, 2 and Zeros is I find they frequently experience kernel panics, especially when they're quite heavily loaded. And there's a change that you can make to the config.txt file that stops this from happening. So you want to edit the config.txt file with sudo by/boot/firmware/config.txt. If you scroll to the bottom of this file, you can then add some new directives. The first one is over_voltage equals 6. The next one is force_turbo equals 1. Now, I find that after I add both of these directives, I never experience these kernel panics again. Full disclosure, I've no idea what's causing them. All I know is this avoids them. Now, as we happen to be in the config.txt file for the purpose of this specific project, we also need to enable the UART pins on the Raspberry Pi. And you do this very simply with enable_UART equals 1. After this, just save out your file, and then you need to reboot. The last thing we need to do in terms of setup is to enable something called SPI on the Raspberry Pi. And you can do this with the command sudo raspiconfig, and that will then display this menu. If you come down to interface options and then SPI, you can then select that you want SPI to be enabled. You can then just click OK when that's done, and then tab down to finish. You can tell that this is working if you now have a file called ttys0 in your dev directory. So you can check for that with this command here. So long as that shows that device, then you know your SPI is enabled. If it's not showing up after you enable that in Raspberry config, just reboot and it should then appear. Now the Raspberry Pi system is set up, we need to connect all of our hardware to our Raspberry Pi. All of that connectivity is shown in this diagram here. So for the LED matrix, you connect the VCC pin or voltage in to pin 4 of your Raspberry Pi. GND or ground goes to pin 14, D in or data in goes to pin 19, CS or chip select goes to pin 24, and CLK or clock goes to pin 23. For the US100, VCC or the voltage in goes to pin 2, TX or transmit goes to pin 8, RX or receiver goes to pin 10, and GND or ground goes to pin 6. You can connect the device to the Pi using absolutely normal jumper wires. Now you'll need female to female jumper wires, and if you haven't got any, you can buy a pack such as this. However, do be careful to make sure that you get ones that are an appropriate length to allow you to arrange the hardware as you need to. If you find that they're not long enough, then you could pick up a reel such as this of male to female wires that you could use as extension cables. You can peel off these wires a small number at a time and then just daisy chain them together in order to make the overall length as long as you need. But now all the hardware is put together, now we can look at the software that we'll need to run the distance sensor and the LED matrix. I've set up this repository in GitHub with all of the software that you'll need in order to run this project. There's one script in here, test_hcsr04.py, that isn't strictly necessary, but I included it anyway. I used this to test out my US100 sensor when it was running in HCSR04 mode. Now Adafruit fortunately provide a Python module that makes this very easy to use. All you have to do is configure it with appropriate definitions for what pin the trigger is connected to and what pin the echo is connected to. In this case, I had the device connected to pins 2 and 3. It then just runs this infinite loop where it calls into the library to pull back the distance, and I then just print that rounded to 1 decimal place, and I loop around that every 2 seconds. Now what I found in my case was most of the time I just received a timeout error. And in the few cases where I did actually get a value back, it was typically fairly inaccurate. I never found a good solution to this. And that's why I switched to using the UART mode. Now the main script in this repository is the one I've highlighted there, called display_distance.py. This again makes use of an Adafruit library that's been developed to drive a US100. There are also other libraries that I make use of here to drive the LED matrix. And I put everything together as a reusable class. So you can integrate this into your code however you like, and please do feel free to modify it for your own uses. The init function here acts as the constructor for the class. Here, I set up the LED panel initially by giving it the SPI definition that I'm connected to. And so long as your D-in port is connected to pin 19, your CS port is connected to pin 24, and your CLK port is connected to 23, then this will work just straight away. I then construct this max7219 object, saying that there are 4 cascaded panels together. My orientation is at -90 degrees, and this will result in the LEDs flowing horizontally. I'm not rotating them at all, and I'm not arranging the blocks in reverse order. Then, for the US100, I'm defining the UART port, and again, this will just work straight out of the box as long as your US100 TX is connected to pin 8 and RX is connected to pin 10. I then construct one of the Adafruit US100 objects with that UART definition. Now, one aspect of this is that I want the display to go off if the distance measured hasn't changed at all beyond 10 iterations of the code. This way, the LED won't be on all the time and it will just save a bit of power. In order to measure this, I set up this DQ object saying it's got a maximum length of 10. I then just add the value 0 as a first element on that queue. I then have a method called read and display. The first thing that this does is that it uses the UART connectivity to call out to the US100 device to get a distance measure. I then push that value onto my queue. I convert the numeric value that comes back to a string, and then I measure the length of that string so that I can subsequently center it within my LED display. I then print that out to the console, just saying what the distance is that's being measured and how long that string is. I really just do this for debug reasons so I can see that the thing is working. I then work out just how many pixels wide the string is. Now most characters in the font that I'm using are 5 pixels wide. So I just take the length of my string minus 1 and multiply it by 5. I subtract 1 because the decimal point is a little bit different. That's only 4 pixels wide. So I take that off the length of my string and then I just add 4 pixels at the end. This then sets up a canvas on the LED matrix. And I then run this check here to see if all of the last 10 values within my queue are identical. So long as they're not, then I proceed. And I use this text function here in order to display the distance on my LED matrix. If the last 10 values that I've measured are all identical, then I just make it display an empty string on my LED display, which effectively just blanks it out. And I then just sleep for a second and allow the code to loop round. At the bottom here I have some test code, so if I run up this class from the command line, it will set up an instance of the distance display object and run it. Now all we need to do is pull all of that code onto our Raspberry Pi. And you do that with this command here, git clone and then the name of the repository. I've listed that in the description below, so you can just copy and paste it in from there. Now in my case, this is going to ask me for some authentication information, but that's only because I haven't made the repository public yet. In your case, this will clone without prompting you for anything. Now all the code is inside the distance_display directory, so let's just move into that. The next thing we need to do is create a Python virtual environment, and we do that with this command here, python -m venv --system -site -packages venv. Now that's created, I need to activate the virtual environment with source venv/bin/activate. Now that's done, I need to install all of the Python dependent libraries that we need for the software to run. Now again, I've made this very easy for you by providing a requirements.txt file, and you can install that easily with pip install -r requirements.txt. Now that's all complete, we're ready to run the code. To run the code, I just have to run this, python display_distance.py. Here you can see that it's reporting a distance of 24.6 centimeters. And since my car isn't going anywhere, that's just going to remain static. But right now, you can't see the LED display. So let me go into the garage and show you all of this in action. Now here, I start backing out of the garage, and you can see that the LED display lights up and it starts showing me an increasing number as I get further and further and further away from the shelving unit. As I make it all the way outside of the garage, the distance sensor gets less and less accurate, and ultimately we'll just start reading the same figure over and over again. And this will cause the display ultimately to switch off, because it will just get 10 of the same number. Now as I start going back into the garage again, it hits this point where the distance sensor picks up the car again. And you can see the number reducing further and further and further. And once it gets under 30 centimeters, this is where I know I need to be really careful. I ideally want to be somewhere between 20 and 25 centimetres away from the shelving unit. So long as I do that, then I know that the car is perfectly placed and that the garage door can close again safely behind it. Now this is all great, but I want this software to run automatically when my Raspberry Pi starts up. In order to do that, I need to set it up as a systemd service. Now I've provided the necessary configuration file for this just here. All you have to do is copy it into the right place using this command here. Sudo cp display_distance.service/user/lib/systemd/system and put a trailing slash on. Once that's there, then you enable the service with sudo systemctl enable display_distance. You can then either start it from the command line here, or you can reboot your Raspberry Pi. In my case, I'm just going to start it from the command line here with sudo systemctl start display_distance. Now that's running in the background, and indeed will run up automatically if I reboot the Pi. And there you go. So now I know exactly how far my car is away from that shelving unit at the back of my garage. And so there is absolutely no chance of me bumping into it at all. But that's it for this video. If you like what you see here, please click that thumbs up button, subscribe if you want to see more, and click that notification bell so you can be notified when I put a new video out. Let me know in the comments if you try this project and how you get on. And if you do have some success with the HCSR04 detectors, please let me know. They're certainly very, very good value. And if you guys have better luck with them than I did, that'd be really good information for everyone else. Also, if you've got any projects that you'd like to see me have a go at in the future, put those in the comments as well. Thanks so much for watching till the end. And until next time, bye for now.